So today we'll discuss permutations. This is a thing that kind of is not a part of linear algebra, but we will need them to define the determinant of a square matrix, and so this is our goal. And so let us discuss permutations first. So it will be section 7, interlude, permutations. So 7.1, symmetric group. Okay, so let us start with the definition. So let X be an n-element set. So since the nature of this set is not essential for us, we will denote its elements just by 1, 2, etc. n. And assume it consists of elements 1, 2, etc. n. So we have the set that consists of elements that are denoted by 1, 2, etc. n. Okay, a permutation is a bijection from this set onto itself. So every bijection of this n-element set onto itself is called a permutation. So bijection, this is a one-to-one mapping. So this is the mapping such that two distinct elements are mapped into two distinct elements, and that for every element here there exists some element here that its image is the element that we selected. Okay, so since X is a finite set, the only thing we need is to specify the images of these elements. So any permutation is completely defined by a table of the form so here we write elements 1, 2, etc. n, and in the second line we write the images, so sigma of 1, sigma of 2, etc., sigma of n, where sigma of 1, etc., sigma of n belong to this set X. Belonging to this set X are pairwise distinct elements. So these are just some elements from the set 1 to n, and so this is the way how we denote permutations. Okay, so then we need to define some more notions here. So the permutation corresponding to the identity mapping is called the identity permutation. So the identity permutation is permutation where all elements are fixed. So 1 goes to 1, 2 goes to 2, etc., and goes to n. Okay, then since sigma is a bijection, defined. So, how do we define this this inverse mapping? So this is the mapping that maps the elements sigma of 1 to 1, sigma of 2 to 2, etc., sigma of n to n. So the permutation corresponding to this mapping is called the inverse permutation. Definition. So let sigma and tau be two permutations of x, then the permutation sigma tau corresponding to the composition of mappings sigma and tau is called the product of sigma and tau. So what does this mean? We have one mapping, so sigma maps x onto itself, or maybe tau maps x onto itself, and then sigma also maps x onto itself. So we can consider the composition. So when we talk about composition of mappings, so this mapping is applied first, and then we apply this mapping. That's why this composition should be applied from the right to the left. So first we apply the rightmost permutation, and then we apply the leftmost permutation. So this is the standard agreement when we work with permutations. Okay, so these are the things that we can do with the permutations. So now let us consider some example. So this is quite simple, so I will not go deep into the details. So consider sigma, which is a permutation of the 5-element set. So for example, 2, 3, 1, 4, 5, 4, and tau is a permutation 1, 2, 3, 4, 5, and I'll put something here, 3, 2, 4, 5, 1. Okay, so these are just two permutations of a 5-element set, and let us find the product. so what is the product of sigma and tau? So I will write them just one by one for convenience. And now I'm going to explain how to find the product using this standard two-line notation for permutations. So I will write 1, 2, 3, 4, 5 here, and then let us look at this permutation. So first we apply this permutation. So here 1 goes to 3, and then 3 goes to 1. So when we apply the composition, then 1 goes to 1. Okay, so what happens next? So here 2 goes to 2, and then 2 goes to 3. So when we apply 2 permutations one by one, then 2 goes to 3. Okay, so here 3 goes to 4, and here 4 goes to 5. So 3 goes to 5. Okay, then 4 goes to 5, and 5 goes to 4. So we get 4 here. So what happens with 5? So 5 goes to 1, and 1 goes to 2. So this is the permutation we get. So this permutation is the product of sigma and tau. Okay, and so let us try to apply them in the reverse order. So sigma tau, 1, 2, 3, 4, 5, 3, 2, 3, 2, 4, 5, 1. So this is the first permutation, and 1, 2, 3, 4, 5, 2, 3, 1, 5, 4. Okay, so what are we going to get here? So 1 goes to 2, 2 goes to 2. Okay, so we get 2. 2 goes to 3, 3 goes to 4. We get 4. 3 goes to 1, 1 goes to 3. So we get 3. 3 is a fixed point. Okay, so 4 goes to 5, 5 goes to 1. We get 1, and 5 goes to 4, 4 goes to 5. 5 is also a fixed point. So we see that these permutations are different. So in general, the operation of multiplication of permutations is not commutative. Okay, so I'm going to make one important remark. So this operation is not commutative, but it is associative. It follows from the fact that the operation of composition of mappings is also associative. Once they are well defined. So when we consider several mappings, we need to control the fact that everything should be well defined. So here there is no problem with this, just because we consider bijections, so they are defined. And the domain of every bijection is just the set X, and the range of every bijection is also the set of X. So there is no such a problem in this particular case. But in general, the fact that this operation is associative follows from associativity of the operation of composition of mappings. Okay, and so now let us now let us consider another example that shows how to find the inverse permutation. So how to find the inverse permutation. Okay, so consider some permutation. Okay, so I will take sigma, which would be 1, 2, 3, 4, 5. Okay, so I'll take a permutation from the previous example. And what is the inverse permutation? So we just need to swap these two rows. So if here 1 goes to 2, then the inverse permutation should send 2 to 1, 3 to 2, 1 to 3, and so on. So we can just swap the rows. 1, 3, 1, 5, 4, 1, 2, 3, 4, 5. And so this is so this table defines the inverse permutations. It's obviously inverse, right? Just because it performs the inverse action on the set X. And the only thing that we can do is to rearrange the numbers such that, so here the elements in the upper line are not ordered, so if we order them properly, then we will get the inverse permutation in the standard notation. So 1 goes to 3, then 2 goes to 1, then 3 goes to 2, then 4 goes to 5, and 5 goes to 4. Okay, so this is what we get, and so we can observe that if we multiply sigma by sigma to the minus 1 in every order, we get the identity. So let us check this. Note that sigma multiplied by sigma to the minus 1 so I will check this. So 2, 3, 1, 5, 4, then 3, 1, 2, 5, 2. So 1 goes to 3, 3 goes to 1, 2 goes to 1, 1 goes to 2, 3 goes to 2, 2 goes to 3. Okay, 4 goes to 5, 5 goes to 4, and 5 goes to 2. Something's wrong. Okay, so the mistake is here. So 5 goes to 4. I should replace 2 by 4 here, and so the standard test is that all numbers should be present in the lower line as well. So since it's a bijection, so if some number is repeated twice, then it is definitely a mistake. So 5 goes to 4 and 4 goes to 5. So we get the identity permutation, and so just in order to be 100% sure, let us multiply them in the reverse order. So 3, 1, 2, 5, 4 multiplied by 1, 2, 3, 4, 5, and 2, 3, 1, 5, 4. So 1, 2, 3, 4, 5. So what do we get here? 1 goes to 2, 2 goes to 1. Fine. 2 goes to 3, 3 goes to 2. 3 goes to 1, 1 goes to 3. 4 goes to 5, 5 goes to 4, and 5 goes to 4, 4 goes to 5. Okay, so that's also the identity permutation. Okay, so this is how it works. I think there is no need to consider more examples or to somehow to be more formal here, just because it is quite simple. But I will make one more remark. So the set of all permutations of X is a group with respect to the operation of multiplication. So we will introduce the notion of a group a bit later, so this is just a remark for those who know what is a group. If someone does not know, this is not a problem at this stage. So, but for those who know, we have an operation, we have an identity, we have a trivial element, then we have so we have the inverse for every element, and this operation is associative. So this introduces the structure of a group on the set of permutations of n elements. So this group is denoted, is called the symmetric group. And is denoted by Sn, so where n is the number of elements in the set X. Okay, so we will not need the fact that this is a group, so we will just use this notation. So those who do not know what is a group can just think of this as a notation for the set of all permutations of n elements. Okay, so 7.2, the sign of a permutation. So we will need some more notions related to permutations in order to define the notion of the determinant of a square matrix. And so, first of all, we need to define the notion of inversion. So, definition, let sigma be a permutation of the n-element set, then a pair ij, where both of them are from 1 to n, and I is different from j, is called an inversion if j is greater than I, but sigma of I is greater than sigma of j. So they cannot be equal because we consider bijections. Okay, so in this case we say that a pair I and j is an inversion. So the permutation sigma is called even if the total number of inversions I of sigma, so I will denote the total number of inversions as I of sigma is even. And similarly, sigma is called odd if I of sigma is odd. Okay, and so one more notation probably and definition. So the number epsilon of sigma, which is minus 1 to the I of sigma, is called the sign of sigma. So it can be either 1 or minus 1, so the sign of every odd permutation is minus 1, and the sign of every even permutation is 1. Okay, let me just write it. Is minus 1, and the sign of an even permutation is obviously plus 1. Okay, and so let me consider some example in order to support this definition. So consider sigma. Okay, so I will consider a permutation of a 6-element set. So 2, 6, 4, 1, 5, 3. Okay, so all elements are distinct in the lower line, so everything is okay. And so let us compute the inversions. So let us list the inversions. So okay. So let us look at the first element here. So the pair, so this is one inversion, right? So the pair 1 and 4, they are in inversion just because 2 is greater than 1. So I will write not elements 1, not the pair 1, 4, but I will write the corresponding elements in the lower line. So what are the inversions? So this pair is an inversion, right? So 2 with 1, then what else? So then all elements here are greater than 2, so there are no more inversions that include 2. Okay, so 6. So 6 is in inversion with every element that is to the right of 6, so we have 4 more inversions with 6. So 6, 4, 6, 1, 6, 5, and 6, 3. Okay, then 4. So we have an inversion 4. 4 is an inversion with 1 right here, and 4 is an inversion with 3, just because 4 is to the left of 3. And then, so there are no inversions with 1 here, just because 5 and 3 are greater than 1, and so then 5 and 3 is an inversion. So these are the inversions, and so let us count them. 1, 2, 3, 4, 5, 6, 7, 8, right? 8. Okay, so we can write down that I of sigma is 8 in this case, and hence sigma is an even permutation. Okay, so we just need to compute the number of occasions where the order where the order of elements in the lower line is broken, and that's exactly the number of inversions. So this is also quite simple. Okay, so one more definition. A permutation sigma from Sn is called a transposition if there exist I and j that are distinct elements from 1 to n such that sigma of I equals j, sigma of j equals I, and sigma of k equals k for, okay, I'll better use the letter L. Sigma of L equals L for every L different from I and j. So what does this mean? This means that 1, 2, etc. n minus 1 n. So, sorry, I need to mark the elements I and j somewhere. So 1, 2, etc. I, j, n. So all elements different from I and j are fixed, and so I is mapped to j and j is mapped to I. So this is how transposition is organized. So in fact, this just means that we swap these two elements. So the only thing that is done here is just swapping two elements, swapping a pair of elements. So such permutation is called a transposition. Okay, and so let me prove a proposition. So any transposition changes the sign of a permutation. So what does this mean? So this statement is quite simple, but so let us prove it. So consider a permutation sigma and a transposition tau. Okay, so we need to prove that epsilon of tau sigma is different from epsilon of sigma. So this is what we need to prove. Okay, so assume first that tau swaps a pair of neighboring elements. So tau has the form 1, 2, etc. I plus 1, n 1, 2, I plus 1, I plus 1, I, etc. n. So what happens when we apply tau to sigma? So this means that, so let us consider sigma, sigma of 1, sigma of 2, etc., sigma of n. So what happens to this permutation? So we just swap the ith element and its neighbor, right? So if we apply tau, 1, 2, etc., n, I plus 1, 1, 2, I plus, I need to be more careful here. One, 2, I plus 1, n. So what do we get here? Sigma of 1, sigma of 2. So here we get sigma of I plus 1. Here we get sigma of I, etc., sigma of n. So that's because we swap these two elements, right? Okay, and so what about the number of inversions here? So let us compare the number of inversions here and the number of inversions here. So the only change of order is between the elements sigma of I and sigma of I plus 1. So this means that the number of inversions is either either it decreases by 1 or increases by 1. So this depends on whether this element is greater than this element or not. So because all other pairs remain in inversion or remain in or are still not in inversion. So the only thing that changes is whether the pair of sigma of I and sigma of I plus 1 is in inversion. So when we apply tau, the only thing that changes is whether sigma of I and sigma of I plus 1 are in inversion. Hence, the number of inversions, so I denote it by I, hence the number of inversions either increases by 1 or decreases by 1. So this changes in both cases. This changes the sign of sigma. Okay. Now let us assume that the permutation, the transposition we apply swaps the neighbors that are not neighboring. Assume now that tau swaps the elements I and j such that there are s elements in between. So this means that j is something like I plus s plus 1 or something like this. That's not essential. Okay, so let us assume that there are s elements in between. So tau has the form 1, 2, etc. I, j, n. So I, 1, 2, etc. j, I, n. And so we have s elements here in between. Okay, so how can we do this? And now we need to apply this permutation, we need to apply this transposition to our permutation sigma. So sigma has the form 1, 2, etc. I, j, n, sigma of 1, sigma of 2, etc. sigma of I, sigma of j, sigma of n. Okay, so we need to swap these two elements. Okay, what happens when tau is applied? So let me sketch the diagram. It's much more simple than write it and explain it in words. So we have sigma of I, then we have S spaces, and then we have sigma of j. Not spaces, they are occupied by some elements, but that is not essential. So we need to swap these two elements. How can we do this? We can first swap these two elements, then these two elements, then these two elements, and so on. So we move sigma of I to this position, finally, sigma of I, right? So when we do this, we swap sigma with S elements. So when we move sigma of I to the right, we swap it with S elements. Okay, and then what needs to be done next? So next, we need to move sigma of j to the left. So then we swap sigma of I with sigma of j, then sigma of j, which would be here with its neighbor, and so on. So we need to move sigma of j here. So how many operations of this kind do we make when we move sigma of j there? So we swap it with all these red elements, so we have S red elements there, and we swap sigma of j with sigma of I, which is now here. So this means that we make another S plus 1 swaps when we move sigma of j to the left. We make S plus 1 swaps. So And each swap is just a transposition of two neighbors. So is a transposition so it changes the sign, as we proved before. And so we make S swaps when we go to the right, and then we make S plus 1 swaps when we go to the left. So hence, in total, we change the sign to S plus 1 times. This means that the sign changes. So this proves our proposition. Okay. So once again, the logic is that when we swap a pair of neighbors, we obviously change the sign of a permutation, and so any transposition of not neighboring elements can be expressed as a sequence of permutations of neighboring elements. And we just need to count the number of permutation of neighbors that we need to make in order to realize this permutation and in order to realize this transposition. And it appears that the number of transpositions of neighbors that we make is always an odd number. It is equal to S plus 1, where S is the distance between I and J. And so that's why any transposition always changes the sign of a permutation. Now we need one or two more rather simple propositions. Or maybe I will start with one remark. So every permutation can be obtained from the identity permutation by a sequence of transpositions. So we just swap elements pairwise, and we do it until we get our permutation. So obviously this can be done in many different ways. So there can be different sequences that lead to the same permutation sigma. But so the sign of a permutation can be defined as -1 raised to the power equal to the number of transpositions we need to apply. To get to get sigma from the identity. If we use this definition, it is not obvious that the sign is well defined. So one can, in theory, it could happen that one sequence of transpositions gives one sign and another sequence of transpositions gives another sign. But we know that the notion of the sign is well defined just because we define it as the number of inversions, which is unique. But nevertheless, sometimes it makes sense to think of the sign as the number of transpositions we make in order to obtain our permutation. Okay, so now I'm going to formulate and to prove a couple of propositions. So if n is greater than 1, then the number of even permutations equals the number of odd permutations. Okay, so let us prove this. So if n is 1, then there is just one permutation or one element, which is the identity, right? So if n equals 2, then there are 2 permutations. What are these permutations? So the first is the identity, and the second is transposition. So this permutation, so the first one is, of course, an odd permutation, and this is an even permutation, so this works in this case. Okay, so assume now n is greater than 2. In this case, if sigma 1 and sigma 2 are both even, there exists I greater than 2 such that sigma of I is different, sigma 1 of I is different from sigma 2 of I. So what does this mean? That the images of all elements starting from 3 cannot be the same for these 2 permutations, because otherwise since they are different, they should differ somewhere, and they can differ only in the beginning. So they are the values of the images of the mapping sigma should be different for 1 and 2, and so in this case they cannot be they cannot be both even, right? Just because we can either keep these elements ordered or we can swap them, right? So there are no other options. Okay, so there exists an element such that sigma I is different, sigma 1 of I is different from sigma 2 of I. Okay, so denote the number of even permutations in Sn by E of n, and the number of odd permutations by O of n. Okay. So consider all even permutations and apply a transposition that swaps 1 and 2 to all of them. So we take an even permutation and we swap the first two elements. So so according to the statement that we proved before, all permutations that we get by doing this are odd, just because each transposition changes this sign. Okay, and moreover, they are different. Because for each pair, there exists the element I greater than 3, as we proved before, such that sigma of I, sigma 1 of I, is different from sigma 1 of j. So when we swap the first two elements, these elements also remain different. So the permutations we get are also different. So what does this mean? This means that from every from every even permutation we get an odd permutation, and therefore the number of even permutations is greater or equal the number of odd permutations is greater or equal than the number of even permutations, right? Just because from every even permutation we get an odd permutation, and all of them are different. Okay, similarly, we prove that the number of even transformations is greater or equal than the number of odd transformations, just by taking even transformations and doing the same. Okay, thus the number of odd transformations is the same as the number of even transformations, and this proves our statement. Okay. And now one more proposition. So let sigma be a permutation of an n-element set, then the signs of sigma and sigma to the minus 1 and the inverse permutation are the same. Okay, so let us prove this. So let sigma be obtained from the identity by a sequence of transpositions. So what does this mean? This means that sigma is tau s minus 1, etc., tau 1 multiplied by the identity. We can avoid writing identity here just because it changes nothing, but just for that's just okay. So every permutation can be obtained from the identity by a sequence of transpositions, and the inverse to, and since any transposition swaps the two elements, it's self-inverse, so it's inverse to itself. So every transposition is inverse to itself. So tau I to the minus 1 is tau I. So what does this mean? This means that I can represent the inverse transformation as the product of these transformations, but in the reverse order. The product tau 1, tau 2, etc., tau s equals to sigma to the minus 1. So let us check this. So I'm going to multiply sigma by this product. Tau s, okay, and so since tau 1 is inverse to itself, this is the identity, so we get tau s minus 1, etc., tau 2, etc., tau s. So the product of these two transformations is also the identity, and so by continuing in this way, so we get the identity. So it proves that, so this proves that this product is the identity, and so here, this product is the identity, yes, and this proves that the product of the transpositions is equal to the inverse, and here I'm using the fact that the inverse transposition is uniquely defined, so of course I did not prove this rigorously, but it follows from the fact that the inverse mapping is uniquely defined. So transposition is a mapping. That's why it follows from the corresponding fact about mappings. And so we get the inverse and the number of transpositions, the number of transpositions we need to apply to obtain sigma to the minus 1 is also s, and that's why the sign of sigma to the minus 1 equals the sign of sigma. So I'm using the fact that I'm using the fact that the sign can be defined as the number of transpositions we need to make, and so this number is well defined, so we know that it is well defined. Okay, so this proves that the sign of the inverse for a proposition is the same as the sign of a proposition. Okay, so these are just standard things about propositions, about permutations that we will need in future. So of course one can study the group of permutations further, but we will not do this, and we will discuss skew-symmetric multilinear functions just because we will need them in order to define the notion of the determinant. Okay, so I will start with the definition. A function f that is defined on the Cartesian product of k copies of the space Rn and takes its values in this space in this set of real numbers is called multilinear. If it is linear, with respect to all its arguments. So what does this mean? This means that the two properties are satisfied. So f of v1, v2, etc., v sub I prime plus v sub I double prime, v sub k equals f of v1, etc., v sub I prime v k plus f of v1, etc., v sub I double prime v sub k. So what's written here? All arguments here are just v1, v2, etc., vk, instead of just one argument, that is the sum of vi prime and vi double prime. And so the value of the function on this set of variables should be equal to the sum of the values of f on the set of v1, etc., vk with v sub I prime here in the middle, and the sum of f of the sum of the value and the sum of the value of so okay, once again, so the sum of so the value of f on this set of arguments should be equal to the sum of values of f on this set and this set, right? So it's linear with respect to the ith argument when the other arguments are frozen. Okay, and this and the second property, that f of v1, v2, etc., lambda times v sub I, etc., vk is equal to lambda times f of v1, etc., vk. And this should happen for all lambda from the set of real numbers, for every I from 1 to k, and for all v1, etc., vk from the Cartesian product from the vector space Rn. Okay, so a function that satisfies this property is called multilinear. So in case we have just one copy of the coordinate space Rn, we have just linear function. Okay, fine. This is the notion of a multilinear function, and now I'm going to give one more definition. So a function f from the Cartesian product of k copies of Rn to the set of real numbers is called skew-symmetric. If f of v tau of 1, v tau of 2, etc., v tau of k is equal to minus f of v1, v2, etc., vk for every transposition tau from the set of all permutations of k elements. So what does this mean? This means that once we swap a pair of arguments of our function, then we get a minus here. In this case, a function is called skew-symmetric. So I will make a remark. It follows that f of v sigma of 1, v sigma of 2, etc., v sigma of k equals the sine of sigma multiplied by f of v1, v2, etc., vk for every permutation sigma from the symmetric group of k elements if f is skew-symmetric. That's more or less obvious just because we can obtain every permutation as the product of transpositions, and so for every transposition we get a minus here, and the sign of sigma is just the number of is minus 1 raised to the power that is equal to the number of transpositions we make. So when we apply a number of transpositions, we just get minus 1 to the number of transpositions here. Okay, and so of course this can be taken as the definition of skew-symmetric function, but maybe it is more simple. It is more convenient to use the definition I gave for a skew-symmetric function. So I will need one very simple proposition. That f of Rn to the k, from Rn to the k to R be skew-symmetric, then f of v1, etc., vk equals 0 if v sub I equals v sub j for some I and j. So if there are two arguments that are equal, then the value of this function on this set of arguments is 0. So it's quite obvious that on one hand f of v1, etc., vi, etc., vj, vk. So if these two elements are equal, then on one hand this is the same as f of v1, etc., vj, vi, vk, just because these arguments are equal. And on the other hand, this is equal to minus f of v1, etc., vj, vi, vk, according to the definition of a skew-symmetric function. So so the value on this set of variables is equal to minus the value on this set of variables, and that's why we get 0. Okay, so that's quite trivial. Okay, so then I will need to introduce some notation. So denote the vector where all components are zeros besides a 1 somewhere on the ith position by E sub I. So this is a vector such that its ith coordinate is 1 and all other components are zeros. So this means that vectors E1, etc., En form a basis in the space Rn. Okay, so let us denote these vectors by E sub I. Okay, and now I'm going to formulate an important theorem that characterizes skew-symmetric multilinear functions. So let f from the space of Rn, from the Cartesian product of n copies of the space Rn to R. So here both the dimension of the space and the number of copies are the same. So let f be a skew-symmetric multilinear function. denote the components of a vector vk by a sub k1, etc., a sub kn. Okay. So let C be the value of function on the set of the vectors from the standard basis. Then the value of our function on any set of arguments v1, etc., vn equals C multiplied by the sum of over the set of all permutations of n elements of epsilon of sigma multiplied by the following product: a1 times sigma of 1, a2 sigma of 2, etc., an sigma of n. Okay, so I will denote this by a star. So what do we need to prove? That if f is a skew-symmetric multilinear function such that the number of its arguments is equal to the dimension of the space, then its value can be represented like this. So we take the sum over the set of all permutations of n elements, so we take the component with the number sigma of 1 of the first vector, the component with the number of sigma of 2 of the second vector, and so on. So we multiply all these components, we multiply the whole product by the sign of a permutation, and we add the result over the we add the result for all permutations from the symmetric group of n elements, and we multiply everything by the value of our function over the by the value of our function by the value of our function on the standard basis. Okay, so let us prove this theorem. First of all, we are going to use the property of linearity. So we have a standard basis, so we can represent every vector as a linear combination of vectors from the standard basis. Every vector vk as a linear combination of vectors from the standard basis E1, etc., En in the coordinate space Rn. Okay, so how do we do it? So we know that the components are denoted by a sub k1, etc., a sub kn. So this means that v sub k is the sum where I sub k ranges from 1 to n, a sub k, I sub k, multiplied by e sub ik. So this is what we get here. And this can be done for all k from 1 to n, right? So this is nothing but the representation of every vector as a linear combination of the vectors from the basis. So I'm going to substitute this relation into our multilinear function. So this is f of the sum where I1 ranges from 1 to n, a sub 1 I1 times e sub I1, etc. So the sum where, I'll write the second argument in details as well, a sub 2 I2 times e sub I2, etc. And the last sum has the form the last argument has the form of the sum where I sub n ranges from 1 to n, a n I sub n multiplied by e I sub n. So this is what we get here. Okay, and now I'm going to simplify this relation. So I'm going to use the properties of linearity. So what does this mean? So if I apply consequently the property, these two properties to all the arguments, so I can write down I can write down the value of this function as a huge sum, where the function f would be taken on some set of the vectors from the basis. So why? Just because if some argument is a linear combination of vectors, then first I can apply the first property, and so this means that f of the sum of n vectors is equal to the sum of the images of just these vectors, right? So we can use, when we apply this, the first property n times, we can represent f of the sum as the sum of the values of our function on vectors that are proportional to the basis vectors. And then we apply the second property, and so we move all the constants out of the function. And so finally, what do we get here? So we get the huge sum where I1, I2, etc., In range from 1 to n. So here we get the set of coefficients 1 I1, a2 sub I2, etc., n In multiplied by f of multiplied by the value of function on the set of basis vectors, of the vectors from the basis, e sub I1, e sub I2, etc., e sub In. Okay, so this is what we get. This directly follows from the definition of multilinearity. So we can apply this property to all the arguments separately. So for example, first we apply the property to the first argument, and we represent the value of the function as the sum of the values of the function where other arguments are frozen. So we get the sum over I1 in this case. Then we move to the second argument, and we continue doing this until we get until we reach the last argument. So we can rewrite the value of our function in such a form. Okay, then we can observe that this, according to the proposition that was before, we can observe that the value of f on the set of vectors from the basis is 0 if there are two arguments that are equal. So f of e sub I1, etc., e sub In is non-zero only if all arguments are different. So what does this mean? We have n arguments and they should be different, and so these are just vectors from E1 to En, right? So every index here changes from 1 to n. And so, since all arguments are different, this means that they are just some permutation of vectors E1, etc., En. So this means that the sequence I sub 1, I sub 2, etc., I sub n is a permutation of the sequence 1, 2, etc., n. Okay, so denote this permutation by sigma. And now I'm going to rewrite the formula we get using this observation. I'll denote this formula by 2 stars. The last formula using the observation we just made. So since only the terms that correspond to some permutation are non-zero, we can represent f of v1, etc., vn as the sum over all permutations from our symmetric group of the form a sub 1 sigma of 1, a sub 2 sigma of 2, etc., a sub n sigma of n, multiplied by f of e sigma of 1, etc., e sigma of n. Right? So this follows from the fact that the sequence is just a permutation of, just some permutation of the sequence 1, 2, etc., n. Okay, and now we're going to use the fact that our function is skew-symmetric. That's why its value on this set of arguments can be rewritten as the value on the standard ordered set of arguments, and using the sign of a permutation. So a sub 1 sigma of 1, etc., a sub n sigma of n, multiplied by epsilon of sigma, and multiplied by f of e1, e2, etc., en. And according to our notation, so c is just the value of our function on this set of variables. So we can rewrite this formula as c multiplied by the sum over the set of all permutations of epsilon of sigma multiplied by a sub 1 sigma of 1, etc., a sub n sigma of n. So this proves the formula, but this is not yet the proof of the theorem, just because we managed to prove that if such function exists, then it has this form. So we proved the uniqueness of such function if it exists, then it has the form that is specified in the theorem. So now we need to prove the existence. Now we need to prove that the formula that we use really defines a multilinear, a skew-symmetric multilinear function. Okay, so first we will check the linearity. So f of v1, etc., v sub I prime plus v sub I double prime, and so on v sub n. What does this mean? So it is, according to our formula, it is c multiplied by the sum over all permutations of epsilon of sigma, so epsilon of sigma multiplied by a1 sigma of 1, etc., I minus 1 sigma of I minus 1. And what are we going to have on the as the ith factor in this product? So we are going to get the ith component of the sum of two vectors. So it would be a sub I sigma of I prime plus a sub I sigma of I double prime, and multiplied by the remaining part of the product. Okay, and so we can expand this product, and so obviously we get c multiplied by the sum over all permutations of epsilon of sigma multiplied by a1 sigma of 1, etc., a prime I sigma of I, etc., a n sigma of n, plus the same sum corresponding to the second term. So epsilon of sigma multiplied by a1 sigma of 1, etc., a double prime I sigma of I, a n sigma of n. So we see that this is exactly the sum of the values of our function on the sets of arguments v1, etc., v I prime vn plus f of v1, etc., v I double prime v n. So this proves that the first property is satisfied. And now we need to prove that the second property is satisfied as well. Okay, so f of v1, etc., lambda times v sub a vn. So according to our formula, it is the sum where sigma ranges the whole symmetric group of epsilon of sigma multiplied by a sub I sigma, a sub 1 sigma 1, etc., then lambda multiplied by a sub I sigma of I multiplied by the remaining part of this product. And obviously this is equal to lambda multiplied by this sum, which is just lambda multiplied by f of v1, etc., vn. So the second property is also satisfied. Okay, so we proved that this formula defines a multilinear function. And now we need to prove that this formula defines a skew-symmetric function. So we need to apply a transposition and to look what happens if we apply this transposition. So consider a transposition tau from our symmetric group. So what is f of v tau of 1, etc., v tau of n? So this means that we take the sum of all permutations in the symmetric group, where we take the sign of sigma and multiply it by a1 of sigma tau of 1, right? Just because we apply this permutation to this set of arguments. A n sigma tau of n. So this is what we get here. So in every element here we are going to have the product of our permutations. And now denote the product of these two permutations as rho. So rho would be the product of sigma and tau. It also is a permutation from the symmetric group, and since they differ by transposition, we can say that the sign of rho is different from the sign of sigma, right? Just because they differ by transposition. But if sigma ranges the whole symmetric group, then rho also ranges the whole symmetric group. So every permutation can be represented, every permutation from this group can be from this set, I will use the word set, can be represented in this form as where sigma is arbitrary permutation, right? Okay, so our formula can be rewritten in the following way. So 3-star formula can be rewritten as C multiplied by the sum over rho, which takes its values in the symmetric group of sigma of epsilon of sigma multiplied by a1 rho of 1, etc., a n rho of n. Okay, and now we replace the sign of sigma by the sign of rho, so it would be minus C multiplied by this sum epsilon of rho, a1 rho of 1, etc., a n rho of n. And so this is, so here we just change the notation, so we use the letter rho instead of the symbol sigma, so and this is exactly minus f of v1, etc., vn. So we see that when we swap a pair of arguments, we get the same value of function, but with a minus. So this proves that our function is skew-symmetric, and so this proves the theorem. Okay, so now we have everything that we need in order to define the notion of the determinant, and so the next couple of lectures will be devoted to the study of the notion of the determinant of a square matrix and its various properties. Okay, so that's it for today.